Let's consider a baseball being hit straight up and being caught 5 seconds after it's hit. Now we're going to call this relatively dense. We're going to neglect aerodynamic drag so that we can use our free fall equations. And we're going to ask, what's the initial velocity if this is the case? Well, let's go ahead and draw a little diagram and say, start, I have some initial velocity that I don't know that I'm trying to find. But I can say my initial position will be 0. My initial time will be 0. And my coordinate here will be y is positive going up. During this process, it's feeling an acceleration downward that's equal to 9.8 meters per second squared. So that's g, the gravitational acceleration near the surface of the Earth. We can then have, after some amount of time, this comes back down to where it started. And so we can have my final position is where we ended up at with my final time of 5 seconds. So the initial velocity of the ball, we need a constant acceleration equation that relates these two things. So I'm looking at my constant acceleration or my free fall equations. And I'll say that my final position is equal to my initial position plus my initial velocity times time minus 1/2 gt squared. And here the negative has already taken account of the fact that my y direction is positive going up and my gravity is opposite that, it's coming down. So I can plug in the things I know, zeros here, and we get 0 is equal to, here I'll write the 0 again, why not? V naught, this is what I'm trying to find, times 5 seconds minus 1/2 times 9.8 meters per second squared times 5 seconds squared. So that's one equation, one unknown. My tendency is to solve these algebraically first and only plug in numbers at the end because I find that's less error prone for myself. But many students find that it's easier to plug in the numbers so that they can more easily identify the one thing that they don't know and solve for that algebraically that way. So you can move this term to the other side, divide it by 5, and you should get that my initial velocity for 5 seconds worth of goes up, comes back down. It had to have been traveling at 24.5 meters per second initially. Now again, this is neglecting aerodynamic drag. So if you have aerodynamic drag, that means it slows it down on the way up, but it also slows it down as it's falling back down. How about how high does this thing go? Again, neglecting drag, we can now use our free fall stuff again. And we'll say, I want to now consider a different situation where my final position is not 0. Now I start going up and my final position is the ball is up here. So we start there and my final position is what I'm trying to find. So the maximum height at that position, we have to know something else about the position, and this is going to be a handy thing. As it's going up, it has a positive velocity. As it's coming down, it has a negative velocity. And so between going up and going down, we're going to end up with some 0 velocity because we were positive, we end up negative, we have to pass through 0. So at that peak there, we end up with a final velocity here at the peak, at the highest height of 0. And so now we can say, still this stuff is true. My initial position and time. I don't know my final time, but I do know my acceleration still, and I know my initial velocity now from the previous problem. So let's go ahead and try writing one of those equations. This one looks like it's going to be the most useful. My final velocity squared, that's the thing I want, is equal to my initial velocity squared, that's something I know, minus 2g times y minus y naught. We can plug in the stuff that we're trying to find. And actually, I misspoke. This final velocity is not what we want. This we know, it's 0. What we want to find is we want to find my final position. My initial position is 0. We can solve this for my final position. Here I'll again show plugging in numbers ahead of time. 24.5 meters per second Square that minus twice gravity, 9.8 meters per second squared, and then times y. And so this is one equation, one unknown. Move this whole term to the other side, divide by twice 9.8, and you should get a final height for the maximum height that this thing reaches of 30.6 meters. So that's as high as it gets. How long does it take to reach there? Using the same information from our previous setup, we now need an equation that gives us the time. So we'll say that my final velocity is equal to my initial velocity minus gravity times time. Solving this for time, we get the difference between initial and final velocities divided by gravity. So this is v minus v naught divided by negative g. So again, I've subtracted v naught from both sides. That gets me v minus v naught. And then I've divided both sides by negative g. So we have, this is my equation. I'll plug in the values. 0 minus 24.5 meters per second. And then divided by negative 9.8 meters per second squared. Plug that stuff in, and you get a final time of 2.5 seconds. And this probably isn't terribly surprising, given that we catch it after 5 seconds, and it spent half the time going up, and then the other half of the time coming down. Lovely. How long does it take to reach the maximum height? We did that. What's the acceleration at the top of the path? This one, I don't actually have to do much calculation. We're using constant acceleration. So the acceleration at the top of the path is equal to the acceleration any point in this path. It's going to be 9.8 meters per second squared downward. Remember, it's a vector quantity, so you need a magnitude and a direction. If I want to show this as a vector, we can put a little arrow over the top. How about what's the velocity when it's caught? Well, you might expect, since it's being accelerated equally, it would just be the same velocity you started with, but now negative. But we can show that. So now we'll say my final velocity is equal to my initial velocity minus gt. And now we're considering not the ball going up to the top of the path, but we're considering the whole thing as it comes back down. So now my time is that full 5 seconds, and we can plug in my initial velocity, 24.5 meters per second, plug in my gravity, 9.8 meters per second squared, and plug in the time of 5 seconds. And you will indeed get negative 24.5 meters per second. So that's 24.5 meters per second downward as your final velocity when you're catching it.